Welcome back, and today we're going to be talking about the final differentiation rule that we will be introducing in this class, and that's called the chain rule. The chain rule is this rule which tells us how to deal with situations where we have a composition of two functions, one function inside of another. So let's state the chain rule and let's practice using it. So to set the stage, let's try and figure out how we would find the derivative of a function such as f of x equals sine of x squared. We know how to find the derivative of sine if it had only an x inside, not an x squared. Side would be cosine with just an x inside. The derivative of x squared, we also know how to take the derivative of that. By power rule, that would just be 2x. So let me state the chain rule. Now, I will be honest with you. I personally don't find this statement of the chain rule to really illuminate what you actually have to do to calculate the derivative in practice. So I'm just going to write down this chain rule, and then I'm going to switch gears a little bit, and I'm going to describe to you how I actually practically think of calculating the derivative of a composition. Here's the formal rule. You want to find the derivative of a composition, g of h of x, maybe. To do that, the first thing you do is take the derivative of g and put the inner function, h of x, inside. Then you calculate the derivative of the inner function, h, and you take the product of those two quantities. So let's have a look at what this rule actually looks like in practice. And I'm going to give you a big disclaimer. This rule can be a little tricky when you're first starting to learn it. So if you're watching this video, if you're trying some exercises and it's not really going well in the beginning, don't worry about it. It's totally normal. Just need to practice, maybe try looking at a few other perspectives on the chain rule, and eventually it will begin to click. So on Canvas, I will be posting some other videos from other creators in case they have a way of thinking about it that connects with you more. So the first thing that I'm going to try and do is I'm going to try and identify in this expression which function represents the inner function and which function represents the outer function. Now I'm noticing that there are two sort of main basic functions present and happening in this expression. One function given by sine, one function given by x squared. So the question that I first ask myself is, of the two functions present in this calculation, which function is inner and which function is outer? To answer that question, I'm going to note the fact that in the function that I was given, the x squared has taken the place of x in sine of x. So the function that does the replacing, the function which replaces x, is the inner function. The function whose x got replaced, the function which in this case is literally on the outside, that function is the outer function. So now that I've done this, I'm going to ask myself a couple of different questions. The first thing that I'm going to ask is, what is the derivative of the outer function? What is the derivative of sine of x? The derivative of sine of x, we know, is cosine of x. So what I'm going to do next is I'm just going to go in, and where I've written down this statement, I'm going to just erase x. And I'm going to leave a blank spot there. And I'm going to say something like, the derivative of sine is cosine. I'm going to make a note that the inner function is x squared, and then I'm going to make a note that the derivative of the inner function is 2x. Once you have these three components, the derivative of the outer function, the inner function, and the derivative of the inner function, you have everything that you need to put the derivative of f of x together. To put together the derivative of f of x, first, take the derivative of the outer function, cosine of blank. Cosine of blank, since we erased the x. Now in the blank, what you're going to put is the inner function. The inner function x squared. Then you're going to multiply by the derivative of the inner function, 2x. This is the derivative of the composition sine of x squared. The derivative of sine becomes cosine, and x squared just sort of hangs around. But then you multiply that by the derivative of the x squared. You multiply that by 2x. Now, just in case you're curious how this compares to the result which is given in the rule, the g prime with these parentheses, that is the derivative of the outer function. The h of x is the inner function, and the h prime of x, is the derivative of the inner function. So comparing what's in the rule to what we got in the example, g prime would be cosine of blank. X squared would be h of x, and 2x would be h prime. Let me demonstrate this thought process to you again. We're going to do a lot of examples. So in this case, I have this huge mess, x squared plus x plus 1, quantity raised to the power 7. So in this case, I'm going to ask myself, what is the derivative of something to the 7th power? I'm going to go back in my mind and say, well, the derivative of x to the 7th power was 7x to the 6th power. So the derivative of thing to the 7th power is equal to 7 times that thing to the 6th power. Not x to the 7th power, but blank to the 7th power. Not 7x to the 6th power, but 7 blank to the 6th power. So that was the derivative of the outer function. The inner function is x squared plus x plus 1, and the derivative of the inner function is just 2x plus 1. So how am I going to put together the derivative of the function f of x? I'm going to take the derivative of the outer part, 7x to the 6th power, and I'm going to put the inner function into the blank. And then I'm going to multiply that by 2x plus 1. So notice that when you have the derivative of a composition of two functions, the unsimplified answer always contains a product. So if you're calculating the derivative of a composition and your unsimplified answer doesn't have a product, that's a sign that something has probably gone a little bit wrong. What if you have cosine on the outside and e to the x on the inside? What's the derivative of the outer function? The derivative of cosine. Cosine of what? cosine of just blank. The derivative of cosine is negative sine. Negative sine, for now, just of blank. What's our inner function? What function is taking the place where x would normally be? The inner function is e to the x, and the derivative of the inner function is likewise e to the x. So to find the derivative of the composition, I'm going to take the derivative of the outer function, negative sine, and in the blank, I'm going to put the inner function. And I'm going to multiply that by the derivative of the inner function. Product. Let's try it again with the derivative of f of x equals the square root of 3x minus 6. This time the function on the outside is the square root. Not necessarily the square root of x, but the square root of blank. We could also think of this as blank to the power 1/2. Now what's the derivative of the outer function? What's the derivative of square root? What's the derivative of blank to the 1/2? The half comes down, and the power changes to negative 1/2. Now what function is on the inside? What function is taking the spot where x would normally be? What function was actually under the square root where the blank used to be? The inner function is 3x minus 6. And the derivative of the inner function is just the constant 3. What then is f prime? F prime of x is equal to the derivative of the outer function, which is 1/2 blank to the power negative 1/2. But in the blank, we put the inner function. Then multiply that with the derivative of the inner function. Now sometimes it can get a little bit hard to see which function is on the outside and which function is on the inside. For example, here we have the derivative of f of x equals 1 over x squared plus 1. There's not really any apparent inside or outside function to me right now, but it might become more clear if we just rewrite this function a little bit. I'm going to rewrite this function not in terms of a reciprocal, but in terms of x squared plus 1 to a power. Now, visually, we can actually see a function on the inside and another function on the outer layer. The outer layer function is given by power negative 1. So the derivative of the outer function would have negative 1 come down, and then that power would decrease to negative 2. The inner function is the function that's literally on the inside. So x squared plus 1. The derivative of the inner function would be, in this case, 2 times x. So what is the derivative of the composition? The derivative of the composition would be the outer function's derivative with the inner function placed in the blank, and multiply that by the derivative of the inner function. Now in this case, Once again, the inner and outer functions are really not that apparent, but there is not this trick that can be used to make it more clear which function is on the inside and which function is on the outside. There are two sort of basic functions at play here. There's a function sine of x, and then there's our standard exponential function e to the x. Now notice that in the function f of x, the sign has replaced the x in e to the x. And that's a sign that sine is the inner function. The inner function is the function which replaces x. The outer function is the function which has e to the something. Now we know that the derivative of the exponential, the derivative of e, is just e again. The inner function we have identified as sine x, and the derivative of the inner function would therefore be cosine x. So then what's the derivative of the composed function f of x? I would take the derivative of outer, and I would place sine x in the blank. And then I would multiply that by the derivative of the inner function. Now this situation that we saw in the previous video of having an exponential base and then having some function up where x would normally be, this occurs often enough that I think it deserves special separate attention. This is a really common situation, especially if you're planning to take differential equations at any point. Let's find a general formula for the derivative of e to some function. Let's just call it g of x. Now, just as in the previous example, in this setup, the outer function is given by e to the something. And the derivative of this outer function is just again e to that something. The inner function is the exponent, in this case just generically called g, and the derivative of the inner function is something that we would symbolically call g prime of x. How therefore would I write the derivative of the function f of x? The derivative of e to the power g of x. This would be equal to e to the power g of x. That much hasn't changed. It's just that now that is being multiplied by g prime. So I think it can save some time if you get this in your mind, that the derivative of e to some function is basically just the same thing that you had before, except that you multiply by the derivative of the exponent. To show you a situation where that can save time, let's consider the following exercise. We're asked to find the derivative of the logistic function, which is given by f of t equals 1 divided by 1 plus e to the negative t. This is a fantastic function, and it's used in lots of different applications. For example, you can modify this function so that it represents long-term population growth. Another application that I've seen of the logistic function is to do things like machine learning. This function can be used, for example, to help to train computers to auto-detect spam. It's quite beautiful. So let's find the derivative of this logistic function. We have a couple of different options. One option would be to find the derivative using the quotient rule, but it's also possible to find the derivative using the chain rule, and since we're in the chain rule section, let's go ahead and take that approach. I'm of the opinion that it can be slightly faster anyway. So let me go ahead and rewrite this expression not as a reciprocal, but as 1 plus e to the minus t to the power negative 1. In this case, the outer function is the function which is literally on the outside, and the derivative of the outer function would bring that power down and then decrease the exponent to minus 2. The inner function would be this 1 plus e to the minus t, which took the position inside the parentheses, literally on the inside. Now the question is, what is the derivative of the inner function? What is the derivative of 1 plus e to the negative t? Now we know that the derivative of 1 is just going to vanish, because 1 is just a constant. So the really important question is, what's the derivative of e to the minus t? And to answer this question, this is a great opportunity to use the formula from the previous page. The previous page says that if you want the derivative of e to the something, copy-paste the e to the something, and then multiply by the derivative of that something. So I'm going to copy-paste e to the minus t, and I'm going to multiply that by the derivative of minus t. So what's the derivative of minus t? That's just the constant multiple, negative 1. So now I have all the components that I need to put together the derivative of the logistic function. We have the derivative of the outer function, which is negative 1 times blank to the negative 2. In the blank, let's place the inner function, which is 1 plus e to the minus t. And then we can multiply that by the derivative of the inner function, negative e to the minus t. So here is the derivative. You're welcome to leave it in this format if you want to. If you like, you can also simplify it, but that's optional. For example, minus 1 times minus is going to cancel out. Leaves you with a plus e to the minus t. And then instead of having a power of minus 2, you can move that into the denominator and have a power of positive 2. But feel free to not do that. I would consider that optional. As a final brief exercise, let's have a look at what these calculations look like if you have a table instead of a full formula. And I'm of the opinion that it's actually slightly easier to do these calculations when you have a table instead of a formula. Because when you have a table, you can make much more direct use of the chain rule formula. Someone says, suppose that my f of x is equal to g of h of x. Find f prime at 0. Now, as we know, before we can find the value of a derivative at a specific location, such as 0, the first thing that we need to do is get a formula for f prime at x. That formula is given by the chain rule itself. G prime of h of x multiplied by h prime. If I want specifically the derivative at 0, now all I have to do is plug 0 into this equation. So let's use the table to to try and figure out what each of these values is. For example, h prime at x equals 0. And when x is 0, the table is telling me that h prime is outputting negative 14. Now when it comes to this first factor, g prime of h of 0, I am going to have to be a little careful. Because when you're working with mathematics and when you're working with functions, you have to work your way from the inside out. So the first thing that I need to do is I need to figure out this innermost quantity. What is h of 0? H of 0 is given by h at 0 is given by 1 here. When x is 0, h of x is equal to 1. So the last thing that I need to finish calculating this is the value of g prime at the location 1. So looking at the table, g prime, when x is now 1, this is located in the final column, bottom row. G prime of 1 is negative 2. So that would be 28. The instantaneous rate of change of this function, the slope of the tangent line, is 28. Because it's positive, we would also be able to conclude that f of x was increasing at the location where x was 0. That concludes today's material. We introduced our final derivative rule, which is called chain rule. It's a rule for calculating the derivative of a composition of two functions.